When applying force to a spring and pulling the string at a certain length, it will return to its original position upon release, right? In the same scenario, when you push a book on a table, it will not yield the same result. Although the same amount of force is applied and work is generated in both scenarios, the nature of forces acting on the book and the spring is different. The spring force that acts on the first setup represents what we call a conservative force, and on the other hand, the second setup, where book is pushed on top of a table, shows friction force, which is considered to be a non-conservative force. When we talk about conservative force, we are talking about forces that generate work that only depends on the initial and final position of the body. This means that, regardless of which path of force is applied, the body will move from point A to point B, as long as its final position is point B. Given this circumstance, what can we say about the work done by conservative forces? Correct, that is independent on the path it has taken. Examples of conservative forces are spring force, gravitational force, electrostatic force, and magnetic force. To further analyze this type of force, assuming a 1 kilogram ball were to move downward by 10 meters from point A to point B, the gravitational force acting on the ball can be computed using the formula F is equal to mg, which, when we substitute the given and perform the indicated operation, our final answer would be 9.8 newtons. Given this force, what is the work done by the gravitational force? Correct, it is 98 joules, which we get by multiplying force and distance. We mentioned that conservative force is dependent only on the object's initial and final position, and that, regardless of which path you apply the force, as long as your final position is the same, you will get the same amount of work. To visualize this, let us again compare the previous example with this another setup. In our previous example, 1 kilogram ball moves 10 meters downward, which gives us 98 joules. Say that we move the ball 10 meters upwards in exactly the same point A and B, we will get negative 98 joules, right? You will notice that the displacement here is negative, even if the arrow is pointing upward, since we are talking about a system with gravity, which is naturally downward direction. Finally, the ball moves covering the same displacement from point A to point B, we will get the same amount of work. So, we have three computed works here: 98 joules, negative 98 joules, and 98 joules, which when we compute for the total or net work by adding all these three together, our answer will be 98 joules. This shows that the work done by gravitational force depends only on the initial and the final position. I hope we are clear on that. Additionally, we say that conservative forces follow the conservation of mechanical energy, which states that the total mechanical energy on a system remains constant as long as the force acting on the system are conservative forces. This means that the total mechanical energy, here represented as ME, on the system is equal to the sum of its potential energy, or PE, and kinetic energy. In equation, we represent this concept as ME is equal to PE plus KE. Let us see if you can understand which of the following statements this law of conservation of mechanical energy implies. Very good. The potential energy can only be converted to kinetic energy and vice versa on any point on the motion generated by conservative forces acting on an isolated system. Let us now talk about non-conservative forces. These types of forces depend on the path taken by the body and not on the initial and final position of the body. A good example of this force is friction force. Friction depends on the length of the path covered by the body upon reaching its destination. Aside from friction, applied force is another example. Since conservative forces depend on the path, there was no potential energy associated with the system. Thus, it indicates that the mechanical energy on the system dissipates or will lose over its motion. Remember that the work done by non-conservative forces may remove or add mechanical energy in the system. In the next video, I will provide detailed examples and problem solving in order for you to have a clearer grasp of conservative and non-conservative forces. This is Gilmar De Castro, and see you in the next video.